This is what I'm looking for. Okay, so proportional lag controller design. So I'm going to do another controller example. And in fact, this is very similar to the PI controller design that I did over the weekend and sent out. So Friday's lecture.
Which has 2 videos on YouTube.
Which has what? So there's like 3 videos that together take about 45 minutes to watch. So. Anyways, this is very similar to the PI control. So PI control can be approximated by proportional lag control. Instead of adding a true integrator and increasing the system type, which is what including an integrator does, yielding 0 steady-state error for a system and input combination with finite steady-state error. So that would be a PI controller that we, like just like the example that we did. The lag compensator instead reduces the steady-state error by some finite factor in the same instance. So instead of taking a system that has finite steady-state error and yielding 0, like putting the integrator in does, putting a lag compensator in after you do the proportional controller design gives you a finite reduction in steady-state error. An advantage of using a lag compensator instead of an integrator is that it can be instantiated in a passive circuit. So you can actually build a lag compensator using just like inductors and capacitors and resistors. If you want to do a PI controller, you have to use like an op-amp, okay? Which is an active circuit element which requires its own power. So it's one advantage. It's a little bit less complex to do a passive controller. But remember that a lot of our controllers that we'll do nowadays are digital controllers anyway. So the difference between active and passive is not super significant for digital control. Okay, the design procedure. The following procedure provides a starting point for proportional lag controller design. Let's assume the steady-state error design spec is to improve a finite steady-state error by a factor of alpha. So say you've got like a steady-state error of 30% when you do a proportional controller, and you want to improve that by a factor of alpha. So it may be given to you, like in the example we'll do, I'll say improve it by a factor of 10. Or it could be that you have a specific, like I want a steady-state error of 2% or something like that. Then you have to figure out what the factor is. Sometimes the factor is given, sometimes you have to deduce it from another spec. So the first step is to design a proportional controller to meet the transient response requirements by choosing the gain K1 for the dominant closed loop poles to be P1, 2. So this is the same proportional controller design we've done using the root locus. Just choose that gain to get you as close as possible to the transient response characteristics that you desire. Step 2, include a cascade lag compensator of the form of 6.5. So similar to putting in an integral compensator, we're going to put in this lag compensator that has a pole, so PC, so the compensator pole, is negative. So it's a real pole near the origin, typically is negative, you would choose it to be. And then ZC is a real 0 near alpha times PC. So the difference here is we had a 0 and we had a pole before, but the pole was at 0, right? It was at the origin. It was an integrator. So PC was 0 for the integrator. In this case, we're just going to choose it to be some real number that's close to the origin. So it's like almost an integrator, but not quite. And then we're going to have the 0, a factor of alpha further out. And that factor, it's not exactly, it doesn't exactly give you the perfect steady-state error improvement that you're looking for in certain cases. So if you have a position steady-state error, static error constant, KP, if you guys remember that, it's a little bit different than just this ratio. You can figure it out, you can do the analysis, but I think that given the fact that we're going to be doing further tweaking of this based on wanting the speed to improve and increasing the gain anyways, we're probably okay with being, it's a little too early to optimize, I think, to the point where we're like being super precise. Like you would get maybe within 10%, you have like a 10% improvement in your placement if you actually calculated what alpha should be, or what the factor here should be. And you can do that, and the Nice textbook discusses it, and I used to teach it that way. But I think that it's actually premature optimization. So, okay, and then K2 equals 1 is what we start with. So we just say, okay, K2 is equal to 1. We place PC kind of arbitrarily somewhere close to the origin, and the closer we get to the origin with it, the better we get for in terms of our transient response not being affected, okay? But it'll be a slower response too. That steady state error correction is going to be slower the closer you get that to the origin. So it's kind of a trade-off. So for minimal effect on the original transient response design, make sure that this the 0. So if you choose that pole to be super close to the origin, then the 0 is going to be super close to the origin too, right? If you choose the pole to be at negative, if you chose PC to be negative 0.001, for instance, that would be really close to the origin. That would mean that your initial ZC would be negative 0.01. So if you want to have super good fidelity to your original transient response designed in the proportional control design in part 1, step 1, then you can go with that. But your steady state error correction is going to be real slow. It's usually not ideal to do that, so we want to move it a little bit more leftward. We want to move them both leftward. So we'll play with that in the example too, like what happens when you move these around. So then, after you're done choosing where your 0 and your pole go, still having K2 equal to 1 at this point, because if we don't affect the transient response very much, we don't really need to readjust our gain very much. So that's a good place to start, is just K2 equal 1. Use a new root locus to tune the gain K2 such that the closed loop poles are as desirable as possible. This step can often be omitted. So you could, at this point, go back to your root locus and say, okay, how is it affected by my new 0 and my new pole? But remember, the whole idea of picking a pole and a 0 right by each other, right near the origin, is to make it so that they have very little effect on the transient response, right? They're sort of canceling each other's effect in terms of the root locus. So that's this retuning the gain K2 at this point. Not always something that we do. I think I often skip that step. Because oftentimes what we're using in the root locus to look at, like, what is the percent overshoot going to be with this gain, or what's the settling time going to be, that's the second order approximation anyways. For most systems, it's not exact. So you're probably going to need to tweak it based on simulation in any case. So I tend to go straight to simulation at this point. But it's kind of up to you. This is one of those things with the design where it's kind of a technique that you develop and maybe you get comfortable with for yourself. This is like sort of a guideline of ways you could go about it. So, step 4, construct the closed loop transfer function with the controller. So this is the controller here. So this was our original gain controller, our P. And then this is our lag compensator, right? So once you put the lag compensator on there, it is your proportional lag controller. Then you can simulate the time response to see if it meets specs. Tune as necessary. If the steady state compensation is too slow, then move ZC or PC leftward. So remember, the closer we get these to the origin, the better the better our original response's fidelity to its transient will be. However, the steady state error compensation will be slow. So if we move them leftward, we could screw up our initial transient response somewhat, but we're usually willing to do that a little bit. We'll move them leftward a little bit, and we'll see like at what point does the performance sort of balance for us. Like when is the steady state error compensation happening quickly enough, but not screwing up our transient too much. So that's.
So moving left is going to speed up.
It's going to speed up the steady state error compensation, and we're going to see exactly that in our example. Because when we first do it, when we're very conservative at first with the placement, we will get a steady state error response that's very slow, and it slowly corrects. But if we want to speed that up, we move them leftward. And then if the steady state error is too large, so remember, we're not reducing it to 0, we're just reducing it by some finite factor. And that finite factor is approximately ZC over PC, which is, by construction here, alpha, right? So if we want to increase our steady state error compensation, in other words, we want to decrease the steady state error, we move the 0 leftward, and the PC we move rightward, or we just change that ratio. I mean, there are 3 ways you could do that, right? Well, you can change ZC and PC such that this ratio increases. That should decrease your steady state error. So this is the process we use to do this design. It's, let's say, very similar to how we do PI control. My plan currently is to do PD control on Wednesday, and then I'll probably give you guys a bonus PID lecture because we'll wrap it all up. But I won't necessarily hold you responsible for the PID on the final, even though it's the funnest. Yes?
You talk about inserting pole into a system for control, like in actual systems. What are you adding? How do you add a pole to a real system? Great
question. Wonderful question. So you can do that by, so what you're typically doing here is you have a system that has some output that you care about, right? Say we've often used the position of a motor. So maybe there's a robot arm, a single axis robot arm, and one motor attached to it that rotates it, right? So say you want that angle to be 30 degrees or whatever. You can measure the actual angle to be whatever, maybe it's 20 degrees right now. You'd like it to be 30. You compare it to the reference. So there your reference is 30. The actual feedback output is 20. You take that error, the difference, and you feed it into your controller. So the way that actually works is you have your measurement, which is probably like a voltage, right? So you take your measurement, which comes from an encoder in the case of a motor, typically. So you have the position of the motor, and you subtract, so this is typically done in software now. You subtract the position that you want from that, and then you say this is how much voltage, you multiply it by our gain or whatever, and you say this is how much voltage we want to supply to the motor to make it go to the right position. So what you're computing essentially is what input should I give to the motor to make it go to where I want. And if you do this, you could do this in a passive circuit in this case. So you can actually, instead of going into software, you can take the voltage output. Say you had an analog encoder. Let's just imagine this scenario. We had an analog encoder. So it just gave you a voltage that was proportional to the angle. and then you put it into a circuit that was like a bunch of resistors and capacitors. And the Nice textbook actually shows you how to instantiate a proportional lag controller in a circuit. So it'll give you like resistors and capacitors and inductors, and you size them appropriately, and it will compute the error and then scale it by whatever your gains are for your controller, by the sizes of the capacitors and the resistors, and it'll put out a voltage that will probably need to be amplified to go into the motor. So that's the process in terms of like an analog, but we don't typically do an analog controller anymore. Typically instead, we're going to take that measurement, that encoder measurement, we're going to turn into a digital signal. We're going to say, oh, okay, I have a pin 7 is maybe my encoder, you know, my encoder pin's probably like 5 pins, and it gives me, like, this is the current position of the motor. I take that, I say, I want, like the user says, I want 30 degrees. It's giving me 20. I compute then what the controller gain times the error is. So 10 degrees times maybe the controller gains 5. And then maybe there's this differentiator, maybe there's this integrator in there. You do that, you estimate that with some numerical approximation of a derivative or an integral by, say, like summing up errors over time for an integral and taking the difference over time for a derivative term. And then you multiply it all out till you get your voltage that you want to apply to the motor, and then you go from a digital to analog converter and amplify it and deliver it to the motor. Maybe on Wednesday I'll bring a system in and show you guys it working in hardware. I'd really like to. I have like mixed feelings because I also want to cover PD control. I want to do it all. We just don't have time to do it all.
If we move the test to like Friday, or take home.
I've done take home before, but
No.
I'm not gonna do take home. I already declared I would not do a take home final in this class.
You can move the test on like Friday.
If we do an M class, I feel bad for 50 minutes. If we do a take home, I feel bad for weeks. Just weeks.
So this is, yeah, I mean, I think that you're asking really good questions, and I really wish that we had more time to talk about like how to actually instantiate these. And if you take the embedded computing class is all about that. So the embedded computing class that I'm teaching right now, but next year as an elective, it's all about how to take controllers you design and make them into hardware instantiations. So digital ones using controllers. So it's pretty fun. Those are really fun. Okay. Also featuring C programming. Yeah. Musical guest. No. A design example. So this is probably, I mean, this design procedure, hopefully this makes sense, but with these things, it really, you just need examples to kind of show you how to do it. So, let a system have plant transfer function. So it's got a 0, a -10, and it's got a complex conjugate pair of poles. Design a proportional lag controller such that the closed loop settling time is less than 0.4 seconds. So that's a transient response requirement, right? And the step response has steady state error 10 times less than with the proportional controller alone. So I just kind of gave us alpha, right? This is going to be our alpha. So let's just go through the steps. And what I did is I wrote it out for you guys, and I showed like all the plots and all the calculations here. And I recommend that you read through that. But what I'm going to do is I'm going to do it live in Matlab, and you'll have this reference to go back to. So the rest of this lecture is sort of, the reason it's all filled in is it's just for your reference. We're going to follow this process, essentially. We might deviate because I might not remember what I did last night when I did this the first time. So we'll see. So the first thing to do is to define a transfer function object in MATLAB. So, we can do this without MATLAB if we are super motivated. Remember that there are like only a couple ways we know how to find the gain analytically, right? We had the lecture 6.2 or whatever it was on finding the gain. But typically we're going to use MATLAB to find the gain and go from there. I know that there's always concern about, so how is the test going to work because we don't have MATLAB? I'm going to have to be very clever to make it so that you don't need to use MATLAB on the exam. But that's my problem and not your problem. If you understand the process and you know the couple ways to calculate it by hand, which we don't typically do, but I did go over very specifically, and I keep highlighting with a bright red sign that says final exam probably, being able to compute the gain without having MATLAB. Make sure you know how to do that. Yeah, just one more time I'll say that. But we'll use MATLAB because this is really the useful way to learn how to do it. It's not useful to learn how to do it by hand. It's like if we learn how to do calculations on an abacus, not super useful anymore. So, okay. So I start all my scripts off with clear and close all. And then we'll put in a cell here and we'll do like system definition. So our open loop transfer function is this plant without a controller. It's just the plant, right? So our plant is, we're going to use TF instead of ZPK. Why is that? It's not factored, so we don't know the poles. We know the 0, but we don't know the poles without factoring, and we don't want to factor because, not because it's hard, it's just we don't want to. So the numerator is, the coefficients are 1 and 10. 1 and 10. You should, by the way, be able to do, like, I'm not expecting you to be able to write a program in MATLAB during the final exam on paper. I'm not expecting you to be able to write a whole program. But you should know the basic MATLAB tools. If I ask you, how would you find the gain, which command would you use, for instance, or how would you define a transfer function object, something like that, you should be able to know how to do that because we've talked a lot about it. So it's not a programming final. You don't have to write like a for loop or whatever, but you should be able to use basic commands to find stuff. Okay. So this is our transfer function. Did that wake people up? Telling anybody that there's going to be any MATLAB on a final exam just scares everyone. Always.
I'm not scared.
You guys will be fine. Just know how to do the homework and understand the lectures, and then there's no problem. Okay. Okay, so there's our system definition, and we always like to check, right? We always like to check to make sure that this is what we think it is, s plus 10. Okay, so that looks like our transfer function. Good. And our first order of business then is to do a proportional controller, right? So we do that using our locus. We find a gain that gives us the transient response characteristics that we want. So we can just go ahead and do our locus of G. It's nice to open up a new figure to do that. And, oh, the green just does not show up, does it? In any case, we'll just work with the blue side. The green side is symmetrical. So the axis is over here. This is the origin. You can't really see it. But if you take the data cursor and you just take a look at some point here. Whoa. Don't know why that's happening. But if we move it around for different gains, we see that the closed loop pole location that we're at changes, and so does the damping, so does the percent overshoot. We don't have a percent overshoot requirement this time, we have a settling time requirement. The settling time requirement is that it be less than 0.4 seconds. Okay. Remember that when we move our closed loop poles leftward, the settling time decreases. Okay? It happens faster and faster. So we know that, you know, at some point, if we keep increasing the gain and they move over here, we'll probably be good as long as this moves over far enough. Do you guys remember the second order approximation formula we use for that? It's this, right? 4 over zeta omega n. And zeta omega n, you may or may not remember, if you look on a, in the S-plane, say this is your closed loop pole location. This distance, the real part, is negative zeta omega n. So we just want the real part of those poles to be such that 4 divided by that gives us 0.4. And my goodness, did I do this on purpose? If you divide 4 by 10, you get 0.4. 10's a nice number. I can do that division in my head. Yeah, that was on purpose. I make these problems up because the way that I do, so that I don't have to do any actual calculation. So we have, oh, look at that, negative 10 right on the money with that one. So negative 10 plus 6.7i is our closed loop pole location there. So that is our gain that we would associate with the transient response that we desire. So let's just go ahead and put, let's call it our K1, and it equals, so 12.1. When I did this last night, I got 12. So, you know, there's a slight variation every time you do it. Okay, 12.1 is our gain. So we actually have designed a proportional controller. We're like already done with the proportional controller design. We're going to add a lag compensator, but before we do that, we always do want to find the closed loop transfer function for all of these. So I'll do G closed loop and then proportional controller. Feedback. Now our controller is in the forward path, so K1 times our plant, unity feedback, and we've got our closed loop controller. So if I evaluate this, then it'll spit out this closed loop controller, and that's the transfer function for it.
What made you pick 12.1?
I chose 12.1 because the data cursor here, when I was at, actually, is it still up? Yeah. When I was at a pole of negative 10, the real part was negative 10, which was what the settling time, the transient response criterion told us, right? It said for performance, for transient response performance, we want the pole to be having a real part of negative 10. So that is why we chose this. Technically, we could be, whoa, I don't know why that's happening. We could be here too. It's like, it just works if we put it down here. What happens though? Like, what would that correspond to? Well, you can read it right off here. It's right on the 0, so that's when the gain goes to infinity. So we could also get that transient response requirement if we turn the gain to infinity. However, that's going to require a control effort of infinity, which is not a realistic amount of control effort. So if you multiply your error by infinity and you try to supply that voltage to a motor, you will fail, I predict. I mean, I'm not one to say that you can't do, you know, make your dreams come true, but this is one that will not. And also that NBA thing. Okay, so that was my dream when I was a kid. I wanted to play in the NBA. I was really upset because I was like, there are so few people who play in both the NBA and Major League Baseball. It's like, so, like I don't know if anybody ever has. I mean, sometimes people have played football, but like not basketball and baseball. But like at the same time, I didn't want to have to choose. I wanted both. So I gave up on both then. I was like, screw it. If I can't do both, I'm not going to do either. Sorry. I take my name out of the draft. Okay, so we have our choice of gain corresponded to a pole location of -10 in the real part because we wanted our transient response to have a settling time of 0.4 seconds or less. So this is like the minimum gain. If we increase the gain some more, we could also improve it more in terms of the settling time. But we usually aim for just right at the cusp because if you increase the gain more, typically you require more control effort. And more control effort means that you have to have bigger amplifiers and all that. So we tend to want to do minimal amount of control effort if possible. So that's our controller designed for a proportional controller.
Dr. Pointer, will the homeworks walk us through or give us problems that we can do this by hand versus Matlab?
I think that there are some problems in the homework that ask of you to find the gain by hand. I can't remember. However, you can always do it, right? You can always find the gain by hand using the definition. It's essentially based on the magnitude criterion. I think is it lecture 6.2? It's finding the gain or something like that. I called it something specifically about the gain. But the first two ways, the analytic method and then the geometric way, which is based on the analytic method, using like the lengths of the vectors. So those are so you can always try it. So say you have a problem and you say, okay, I don't want to rely on Matlab to find this gain. See if you can find it for some of the homework problems. I mean, you don't have to do it for every one because it's quite tedious, but know how to do it for like one of them at least. Know how to do the method. And that's what I'm going to be looking for anyways, even if you don't compute it quite correctly. If you know what you're doing, that's what I care about. So, yeah. All right, so this is the so proportional controller done. Now we want to do a lag compensator, right? So we're going to go through several iterations of the lag compensator. So I want to call this one lag compensator 1. So this is just like the first one, the naive one based on just, you know, choosing a PC, a pole location, and then multiplying that by 10 because we have an alpha of 10 to get ZC, and then we'll go from there. So let's do that. Let's say our PC, we can choose this somewhat arbitrarily. We know it needs to be close to the origin. And should be negative to yield a more stable system. So let's say we'll do a PC of, I think I started with like -0.1, which is pretty reasonable because we're about to multiply it by 10, right? Because our alpha is 10. So I'll define that. Alpha equals 10. And remember, that came from our steady state error improvement requirement. We didn't look at the steady state error for this proportional controller, but we know that it's some finite value, right? How do we know that's a finite value? How do I know that for a step input, the steady state response is finite, or the steady state error is finite for this plant? 6.7. Yeah, this has how many integrators? How many integrators does 6.7 have? 0. So it's a type 0 system. And a type 0 system with a step input, if you go back to that table for steady state error, you will find that that is a finite steady state error. So we know that. We don't know what it is, but we know that we were looking for a factor of 10 improvement on that. So we're going to have to figure out what it is eventually, but we know we need to design a lag compensator anyways, so we might as well just do it and then look at the steady state errors. So let's try it. And our improvement needs to be a factor of 10, so we'll say alpha is 10. We'll say ZC then is is alpha times PC. And then let's build our compensator. So compensator, I'll call it compensator 1 because we're going to do several of them. So our compensator here is going to be, we can define it, I'm going to define it using ZPK because we already have the zeros and the poles. I mean, we could easily use TF if we wanted it as well. But, so we want ZC for our 0, we want PC for our pole, and then the gain, we're just going to set to 1 now, right? This is going to be our K2 gain. We're going to set it to 1 for now. And in fact, I will explicitly do that so we don't forget about it. K2 equals 1, and I can put my K2 in here just to remember that it's there. We'll come back to it. So there's our compensator. And now we're ready to go ahead and close the loop, right? So G close loop PL1. So this is going to be our proportional lag controller 1, initial design. And so that's going to be feedback of, so K1 is still there. I like to explicitly put K2 in, so no, I'll leave it out. I put it in there, I'm just going to do that. So C1 times, and then you have to make sure you have the plant in there again, right? Unity feedback, so there's the same feedback loop except we have a compensator in there now. Now at this point we could do another root locus. So that was the optional second root locus to look at and see if we need to tweak K2 a little bit. But since we're probably going to go through this iteration several times, I think going to simulation now is probably the right move. So let's do simulation down here. Let's do TA equals the time array. Let's do linspace from 0 to 2 seconds, and we'll do like 200 points or 100 points faster. And then let's just do step responses now. So YP is equal to step of the closed loop system. So G closed loop for our P controller, and then our time array. And then we have also our proportional lag controller step response. So the same syntax again. So those are our 2 step responses. And now let's plot. So let's open up a figure, and we'll plot TA and then YP, the proportional controller's response with closed loop. So then we'll hold on. So I'll do blue, and then I'll do line width, probably 2 for in here. And then I'll do another one of these where I'll do PL1. So this is our lag. This one I'll do red, and then we'll do X label time in seconds, Y label step response, and then we'll do a quick legend just so that we remember which is which. So P controller, and then PL1 controller. Okay, so that should do it. I don't think I evaluated that one. Okay, I'll run it from the top. Yeah, okay. So, oh, we should get a grid going, I think. So,
That changed nothing.
oh, you can't see the grid, yeah. So the P controller and the PL1 controller in red, they have similar transients, and then you see this slow steady state error compensation kick in, right? We kind of expected it to be slow because we were being a little conservative by picking a really small PC first. So now let's design another iteration. And so the things we can do, if we want to speed this up, so we can move the poles in 0 leftward. We can also increase the gain. Those are two things we can do to try to speed things up. If we increase the gain, we're probably going to move this rise time. We're going to shorten the rise time too, which we don't have any reason to think that's bad for this system, so we're probably okay with doing that. We don't even go far enough out here. Even in 2 seconds, we don't see the steady state value that we come to. So we can't quite evaluate that performance yet. But my guess from just eyeballing this is that we're not getting a factor of 10 better than the original transient, or the original steady state error is like, what would you call that? Like 17%, 18%? And the steady state error here, I would say, is still maybe going to be like 3%. It needs to be 1.8%, right? So we're not quite there. We could simulate out further, but we kind of want this to happen faster. Let's just assume that we're like, we want the steady state error to go away faster. So we're going to move these leftward for our second design. So, in fact, I have an idea. Instead of doing this, like the way that I did it in the lecture, I designed like PL1, PL2, PL3. So in your notes, that's what it looks like. But just given time, I think that we'll just, instead of adding more and more layers to it, we'll just tweak our lag compensator 1. Okay? Let's just do that. I think it'll be faster, and we'll get just as much out of it. So when you go back and look in the notes, there will be multiple, and I don't wipe away the old one when I go through it. So okay, so now let's say, okay, I want to be a little bit more aggressive with my compensator. I want to make this thing go a little bit faster. So I'm going to move them leftward. So we know we're gonna multiply PC by 10. So we can just move this one. So say I'll move it to 0.3, negative 0.3. So that means that our 0 is going to be at negative 3. If our closed loop pole, dominant closed loop poles are going to be at negative 10, that's still quite a distance away from them. So it's probably not going to affect them too much.
Slightly different direction than what I had originally planned, so I had to scratch an entire page.
Just can't handle that. Okay. All right. That's better. So let's try it with this. So we moved them leftward. We're keeping the same ratio of 10 between them. And let's keep our gain, K2, at 1, just to see what this looks like, okay? So we'll run it. And it definitely got faster, right? Our settling time, so there's a little weird thing to observe about settling time. Settling time, typically, the definition of it gets really messed up when you use this slow steady-state error compensation, using an integrator or using a lag compensator, because the definition of the settling time is that the time at which the response gets to within 2% of the final value and then doesn't leave it again. So if you have this long, slow ooze to the final value, that often kind of messes with that. However, we're gonna say strict, like we want to be really strict about our settling time, and it's really hard to eyeball this. So let's start to actually compute settling time, compute settling, and we'll also do compute the steady state error. So computing the settling is easy to do with step info, right? So if we use step info and we give it the step response, we're interested in PL1. That's the one that we're actually designing, right? The proportional was just along the way. So PL1, and then our TA. This gives us an object that we can select out the settling time calculation from the simulation. So if we compute this, 0.634 is what we're at, which we want it to be 0.4, so we're not quite there. And let's look at our steady state error. So that's going to be, we can just directly compute that. That's in percentage. I want to do it in percentage. We're going to be at 1.8%. So 100 times the last value in our, it looks like we're now getting to essentially a final value, so we can trust the last value in this step array. So let's do that. So y PL1 end. We want it to be 1, right? It's a unit step, so 1 minus that is going to give us some fraction of 1, and then we want to multiply by 100, and that gives us a percentage. So this should be our steady state error. So 2% steady state error, we want it to be 1.8, right? Because we have about 18 to start, so we want to be about 1.8. So we're getting close, right? With our transient, we're getting close with our settling time. So what we could do, we could try doing something with our moving this leftward more, or we could increase our gain a little bit. So let's try that just to see how we do. Looks like it improved. Settling time is now less than 0.4, okay? So 0.297, and our steady state error is 1.7%, which is less than 1.8, so we met that spec too. So that would be our controller design that would meet the spec pretty well. Now notice that we still have steady state error, right? We knew that going in. We were going to have some finite steady state error. We were just going for a reduction of a factor of 10. So if we wanted to print out our final controller, we would just look at the this compensator, and we would have to scale it by K2, right? So our final compensator is K1 times K2 times, we could even, well, by C1, the current definition. So that's our controller that we've designed. That's it. All right. Good work.